So this is the zero-dimensional global energy balance, or the radiation balance. This is the basic equation that we study whenever we start any climate science or a climate modeling course. So this is the most basic equation, which basically shows the incoming solar energy. This part is the incoming solar energy, and this is the outgoing long wave energy, all in the form of radiation. So the incoming radiation is basically intercepted by this cross section of the earth. So just pi r square is there, and the energy loss from the earth surface is all around the globe on the spherical surface, though. So that area 4 pi r square is there. So basically the incoming solar radiation is balanced by the outgoing long wave radiation. That's what it means. So this is the zero-dimensional energy balance equation. So the image and the equation have been taken from this paper. So this is actually not a good equation to get the accurate values of the temperature or whatever we are interested in, but it gives order of magnitude values, not the exact values, order of magnitude values. Maybe sometimes they may be off by a factor of 2, but within the same order. So this paper explains more what are the things that are needed to get a proper estimate. And also in our YouTube channel Neophysics, we have a couple of videos describing it in more detail, like why this equation is wrong, and what are the other things we need to include to get a proper estimate. But for now this is okay, the order of estimate is fine. This is a very basic calculation we are doing here. In future we'll do more proper accurate calculations, more sophisticated calculations. So for now this is good. So basically this S is the solar constant, which is the incoming solar radiation per unit area at the top of the atmosphere here, whatever the incoming, and this value is about 1367 watt per meter square. Alpha is the Earth's average planetary albedo or reflectivity, and it's about 0.3. This sigma is the Stefan Boltzmann constant, and this epsilon is the effective emissivity of the earth. So usually if there is no greenhouse effect or something, it should be 1, but here the effective from the experimental observations, it has been found that it should be around 0.612 in this equation. And this value accounts for the greenhouse effect observed on the earth at this present time. So these are the values. So if we want to calculate the temperature using these values, we get a value of around 288.15 Kelvin, which is about 15 degrees centigrade. During the ice ages, the average temperature of the globe is around 8 degrees centigrade, or about 281.15 Kelvin. So if we keep all the other things the same, the sigma is the same, it's a constant. The epsilon, if we basically keep this emissivity value constant, and if we want to achieve this temperature, then there should be a different albedo value, or this reflectivity value. So plugging in this 281.15 here instead of this 288, we find that the alpha corresponding to this, if we want a much lower temperature, this is about 7 degrees less than this. So if we want this temperature at the same emissivity value, we should have an albedo value of 0.36555 instead of 0.3. So right now it's 0.3, but if we want to enter an ice age or create an ice age, we should enhance the reflectivity or the albedo of the earth to this value, 0.36555. So then we'll achieve this temperature 281.15. This is the average temperature of the earth. So suppose there is a material X whose reflectivity is 0.85, that is, it reflects 85% of the sunlight falling on it, and assume we cover a Z fraction or a Z portion of the earth with this material X. So rest of the earth will have the usual 0.3 albedo as observed, and some portion of that will cover it with this 0.85 reflectivity material. So if we want to get this 0.36555, which is the value we need to get this ice age temperatures, we'll need to cover 12% of the earth, around 12% of the earth with this material, whatever this material X with 0.85 albedo. If we cover 12% of the earth with this material, then in a few short years, not even a decade, it's pretty fast response. In a few years, we'll get into this ice age temperatures. So that's all we need. Just cover the 12% of the earth with this reflectivity, and we can create ice age on earth. And if we start this process near the polar ice sheets or around the glaciers around the world, this can be even more efficient, as we can exploit the ice-albedo positive feedback effect. That is, once we put these reflectors, there will be reduced solar radiation in overall in the earth system, so that will lead to lower temperatures, especially in the locality where we have put it. There will be lower temperature, that will lead to more ice creation. So if we are putting it near these polar ice sheets and the glaciers, there will be more ice there, and also there will be less melting of the ice during summer. So more reflection leads to lower temperature, leads to more ice, which in turn leads to more reflection, because ice is very reflective, the fresh snow and all. So it can reflect up to 90% of the sunlight, so it will reflect more sunlight. This will further reduce the temperature, this will further lead to more ice creation and less melting. So this is a positive feedback cycle. So if we increase the albedo, there will be more ice created, and more ice will enhance the albedo more, and there will be more ice created. So this positive feedback can continue. This can be a runaway positive feedback effect also. So if we don't want an ice age, if we just want to reduce the temperature of the earth by just 1 degree centigrade, so right now it is 288.15, so suppose we want to achieve less than that, 1 degree less than that, which is 287.15, we just plug in here the temperature in this formula for this albedo alpha. We get a value 0.30963. So this should be the overall albedo of the earth instead of 0.3, to get an average temperature which is 1 degree less than the present temperature. So if we want that, and we cover with the same reflective material with 0.85 albedo, we need to cover the earth with about 1.75% of the earth's surface with this material. So if we cover 1.75% of this of the earth's surface with this material X, then we'll achieve a global average mean temperature of about 287.15. So just for comparison, the total urbanized area of the earth is around 3%. So this is not much. It's like half the size of half the area occupied by the urbanized portions of the earth. And if we increase it, if we cover this 0.85 albedo material with if we cover the 3.5% of the earth's surface with this albedo material 0.85, then we will get a 2 degree drop from the temperature. So we'll end up with 286.15, 2 degree drop. So basically we can place this, in order to achieve this, we can place these reflectors in more cloud-free regions of the oceans, and also on the deserts, and it also will be very effective if we place them on paved or asphalted regions of the world. Or also we can put it in hot spots which show very large global warming signature. So so we can well distribute it, relatively well distribute in different portions of the earth, so that it's not concentrated, the whole area is not concentrated in one place, to get better effect. So so with this effect we can create the ice ages also in just few couple of years. So that's all. Thank you.